Another aspect which we are like very well familiar with, like data models, relational or like non-relational, which one to choose with. So we're not digging too much deep because of very much familiar on this topic. So here is a like quick summary of like different aspects and different use cases that come across this thing. But one very important aspect that we need to be very careful about when we are choosing relational versus non-relational is we don't want to be in a situation where we choose a document or like non-relational and then just keep on doing optimizations like, okay, just introduce some index on it and like then okay, make some join capabilities on it, so on, which will eventually end up creating or like reinventing a wheel of another SQL engine, right? Like ourselves. So that's one thing we really want to recommend about when we are choosing that relational versus non-relational when we are looking at the database. So yeah, with that, I'll hand it over to Om to go over like data storage and examples.
Yeah, so now that we have come across data modeling, data formats, and everything, I'm just going to do a quick summary of the latter half of our chapter. So with data storage engines, we're basically dealing with databases. So we're going to define how they store and retrieve data. And historically, they've been optimized for two different types of workloads, one being transactional and the other being analytical. We're going to contrast them in the next slide. Next slide, please. So OLTP and OLAP were the terms used for online transaction processing and online analytics processing. So OLTP-based workflows are mostly suited to consumer-facing applications where you have to like keep a track of user events or user activity from applications. And in these applications, you would want databases that would prioritize high availability and all the other asset properties that would make it ideal. But reading through the book made me notice that only a subset of these asset properties are actually could actually pass for OLTP-based workloads. So we can have something that's basically available, soft state, and has eventual consistency. This would also work for an OLTP-based workflow. Coming to OLAP, it's completely different from OLTP, where you're dealing with transactions, because OLAP mostly works on viewing data in different dimensions or trying to derive insights from our data. So in OLAP, what you want to do is like, given sales information, you would want to like view it in terms of different regions or different demographics and things like that. And that's when you want to prioritize building structures like cubes or different structures that can let you view this data in a different perspective. And since most analytics queries are aggregation based, OLAP is mostly optimized for aggregation based workloads. Let's move to the next slide. So a key takeaway from the book is that OLTP and OLAP are actually getting outdated now because of three reasons. Well, technology seems to be no longer limited. So you have databases that can support both workloads pretty well. You have like CockroachDB, Apache Iceberg, and DuckDB that actually do all these workloads pretty well. And then you have storage and processing decoupling. So your storage layer can be completely different from your processing layer. You can have like HDFS storage, which would have high availability and great replication. And you might have a thin processing layer that's optimized for whatever workload that's important to you. And then finally, online these days has a completely different meaning. So online used to mean something that's connected to the internet, but now it seems that online is mostly related to data processing speed. So if you're processing data online, that means you're pretty fast with processing data. And then you have nearline and offline speed as well. Let's move to the next slide. So given that we have information on storage engines, let's focus on a pipeline that would get data from sources to targets. So to enable this, we have ETL, which is basically the pipeline that's used to get data from a structured source, like a database, app, or a flag file, etc., to your target data warehouse or any feature store, etc., using three distinct processes: the extract phase where you filter out the data that you're interested in, the transform phase where you basically format this data into what is required for your model or for your target data warehouse or data storage, and load where you just simply load into the target feature store. So let's move to the next slide. So the key takeaways with the ETL section of the book is that ETL makes sense when you have takeaways with the ETL. Move to the next load where you just simply target feature store. So let's move to the next slide. So the key takeaways with the ETL section of the book is that ETL makes sense when you have data that's already structured and it's ready to be filtered out. If you don't want to put the effort to filter out this data, rather than keep this data structured, you might want to use something known as an ELT pipeline, where you basically bring data much quickly into your storage and then transform it into whatever your requirement is later on. And then now companies have been shifting from ELT to ETL because they're finding it tedious to transform at a much later stage. And data vendors today have both options of ETL and ELT available based on whatever the requirement of each client is. Let's move to the next slide. So now that we have discussed on how to get data from one place to another, and also have discussed about storage engines, in the book we discuss about how we communicate using data across different processes in production. So there are three different ways we can have data flowing in our production-based application. So we have passing through a DB where you simply write to a DB. DB and read from we can have data flowing in our production-based application. So using data across different processes in production. So there are three different ways we can have data flowing in our production-based application. So we have passing through a DB where you simply write to a DB and read from another process. And then you have passing through services where you have each process as a service and you have a request-response-based interaction between them for getting your data. And then you have passing through real-time transport, which is basically each process communicating to a broker, which acts like an in-memory store for the latest data received, and every other process querying it would be able to receive the data from this in-memory store in real time. Let's move to the next slide. So the key takeaways from this section is that data passing through a database, data passing using a DB is not a good idea for most consumer-facing apps because every read and write from a database has some latency, and data passing through services works, but on a lower scale, because on a high scale, like for ML-based, in the context of ML-based applications, you might have 1,000 other processes from which you're going to extract features for your ML process. So this is where service-based data passing might not work, and then data passing through real-time transport works for most data-intensive applications. So, but for a small-scale application, you might might not want to push in the effort to use something like Kafka or RabbitMQ. Let's move to the next slide. Finally, the chapter wraps up with like a contrast between batch processing and stream processing. So I think it's pretty much evident what these terms mean. But in the context of ML systems, okay, let's move back. In the context of ML systems, stream processing is primarily used for like getting features that change quickly, like dynamic features. Like given an app like Uber, you would want to get the number of drivers in a location, get the number of users requesting for a ride. That's when stream processing is mostly useful. And stream processing is a more tedious and difficult way of processing data due to the speed at which data arrives and the undefined size of data. So let's move to the next slide where we talk about Gen AI and what's new with data engineering. Nikhil will be taking this forward.
Yeah. So hello everyone. Let's now talk about generative AI and how it has changed the world ever since ChatGPT came out later in 2022. Next slide, please. So with the rise of LLMs, traditional databases struggle with AI workloads and which is leading to emergence of specialized databases. Two types of databases that we are focusing here are vector databases and graph databases. So vector databases are optimized for similarity search, clustering, and nearest. Neighbor queries and are perfect for AI applications that rely on vector-based data. Examples of which are computer vision and LLM. NLP, natural language processing. An example of vector DBs are FAISS, Pinecone, the most popular one, Quadrant, the most trending one, I suppose, and Milvus for graph databases. They're designed for storing and querying complex relationships between data entities and are ideal for applications that involve network analysis, recommendation systems, and knowledge graphs. Examples of graph DBs are Neo4j and Amazon Q, and these are the databases that are now becoming mainstream with the rise of LLMs. Next slide, please. So generative AI has had a great impact on the data landscape. It is essentially transforming how we create, process, and analyze data. With these models generating vast amount of data, traditional data management systems face challenges in handling scale and complexity. Some examples of data that is being created today with these powerful LLMs are Sora and Pika Labs being efficient in creating AI-generated videos, Midjourney, DALL-E, and Stable Diffusion creating images, and we all know how much text that is being created with ChatGPT and Mixtral and all these powerful LLM models. Now, this necessitates a shift in our approach for data management. With these new architecture and technologies, like this, one second. Yeah, like distributed database and cloud network storage solutions, the impact of Gen AI on the data landscape is quite profound. It is now forcing us to rethink about our data strategies, from data ingestion and processing to analysis and visualization of our data. Next slide, please. So, unstructured data has been in the limelight ever since in AI in general, and unstructured data essentially includes images, video, and text, and is playing a pivotal role in Gen AI application. The search in unstructured data is largely driven by the LLMs, such as BERT and other transformer-based architectures. LLMs require specific methods for storing, processing, and analyzing unstructured data. They are also pushing the boundaries of conventional data management systems, prompting the creation of innovative architectures. And through this graph, you can see that over the course of period, there has also been an exponential rise in unstructured data that are being stored in modern data. So, in a sense, the growth of unstructured data and the advancement of LLMs are intertwined. Each driven the other forward in the cycle of innovation and growth. And this time, dynamic is essentially reshaping the landscape of data management and Gen AI applications. Next slide, please. So, we have all been using generative AI tools and applications quite often. And over here we are is tailored investment portfolios based off of every individual's personal risk tolerance and their financial goals, and give them a more personalized report. In healthcare, Gen AI-powered chatbots, they provide personalized response to the patient's queries, enhancing their overall experience when it comes to booking appointments and all those things. In education, Gen AI is being used to personalize the learning experience and the learning path for the Gen AI and Copilot and that. So traditional data platforms struggle with the scale and complexity of Gen AI workloads, and new solutions are emerging to focus on data platforms that utilize generative AI. So that includes Databricks, that offers a unified analytics platform, Apache Spark, providing a scalable platform for big data processing, and Google Vertex AI or Azure AI or Amazon Bedrock that provide cloud-based platform for building, deploying, and managing these models at scale. Thank you.
Cool. This is amazing. I really enjoyed the presentations. So before we go into breakout room, so I was prepare like several discussion questions for today. I'm going to share with you shortly, but I just want to do a little bit of exercise here. So we talk about data flow in this chapter, and data flows, or like whether to use streaming or database to pass data, it really depends on the use case. Like first of all, we use machine learning models, right? We might need to access data to make models to make predictions, and what data flows mode we use depends on how fresh we want the feature to be. So for example, one thing is like, okay, if we want data, if we're okay with data being like a day old, right? Then we just wait for data. We can have 1,000 of ways to like transfer data. If you're okay with it being 1 day old, like you can literally just get like copy and paste. Like you can share on Google Drive or like S3. But like if you want data to be like 10 minutes, like can be at most 10 minutes old, then you would need a different way to pass data. And if you want the feature to be like at most like 10 milliseconds or 100 milliseconds, then the options become a lot more limited. So like another thing, so here let me share this. This is what I how do I do this? Okay, it's desktop one. Okay, can you see my screen?
It's loading.
Yeah.
Yeah, now we do.
So it's using real time, right? You have like an application to produce data. So for it, usually like if you want to just like immediately dump everything to the lakehouse, so maybe you can think of it as like 10, 15 minutes for it to get there. But if you want it to be faster, then you need to access things when it's still streaming. So like say if you want data to be like, if the data is like okay with data being stale for like 10 minutes, 15 minutes, I would say that you can just wait for data in the lakehouse and then do a query on the data. It's like pretty straightforward. But then if you want data to be like really fresh, then you might need to do stream processing. Does that make sense? So you think of like how fast you want to access your data, and if you want the data to be like an hour old, so you don't really streaming, you can just like have other way to move data into the data lakehouse. So usually everything else is like first requirements. So say like if you have an hour, so we have different use cases you can think about, and we can have exercise go into each of these use cases to see which how fresh what features, like what kind of data do you need for these different use cases, and how fresh each of this data has to be. So here's one example how fresh. What features, like what kind of data do you need for these different use cases, and how fresh each of this data has to be. So here's one example. So to determine data freshness, we need to think of like what data does model need, how fast do these values, what does data change, and what is the impact of the stillness, right? Because like if data changes a lot, but it doesn't really impact the model, then you don't really care. So let's go into an exercise here. So you can think like in-store pricing. So say you run a grocery store, and for the items in the store, you want to like determine like how much, like, what's the optimal price for each of the item in the store, right? You don't want it to be like too high because then like nobody's gonna buy it, but you don't want it to be like too low because you lose money. So what kind of data do you think you would need to like do optimal pricing for the grocery store?
I'll say sales data and the price of sales data plus the price, well, including the price of the items.
Is this a baby?
Yeah, I'm in the car. We're on a road trip to Toronto.
Okay. That, I hope the baby is will something as well. So yeah.
I would say, of course, sales data is important, but you may need also more than that. Like you may need some seasonal data to tell you which season you are in, because that way definitely impact in-store pricing and things like that.
But in general, still not very fresh data, right? We're talking like an hour plus on all those data freshness, right? Because we change prices too frequently. I feel like customers would be annoyed. You know, if I shop for 20 minutes and prices are changing after I put something in my cart, that's probably a negative sign.
So I guess in different situations where people are more okay with prices changing. First of all, flight prices change pretty fast, or even like Amazon store, like it's pretty fast. So yeah, so like we definitely.
I think a good example for this is the search pricing that we have in Uber and other similar kind of services, and now even some restaurants or food services are trying to implement similar kind of search pricing. So I think in those cases you will need to have real-time data to decide the pricing, and then those will be different factors that you may want. Like traffic could be one of those reasons, or the amount of people who come to your store or restaurant at that time might be one of the metrics or data points you use here.
Yeah. Sorry.
Oh, never mind. Yeah, no, I was just going to say, I was trying to think about, like, do we, would there ever be a scenario where, like somebody else was saying, if I go into a store and the prices are changing real time, would there ever be a scenario where I'm okay with it? And then I was thinking of, like, Thanksgiving sales, like 10 years ago when people used to still go to the store, or like when there's a new item on the market and let's say like the newest iPhone drops or things like that. And those are occasions where people are okay if the in-store price changes because it's a high demand item or like there's a good sale or things like that. But on a day-to-day basis, I would still say like people assume that in-store prices are sort of fixed, not necessarily always, but over like a week. Like usually if you go in on Monday and then you go in on Friday and the prices change, you're going to be surprised, right? So from that point of view, I would say you could use surge pricing sort of thing for special occasions, but that would probably not be the norm for in-store pricing, or at least that's how I'm looking at it.
I see. So I saw Philip comments about sort of Wendy's is moving to this dynamic pricing, like in store. Like
that was what I was talking about. So Wendy and some other stores are also exploring that idea of doing some dynamic pricing, where store price can change depending on many factors, just like how Uber and other ride-sharing services are currently doing.
And they keep saying it's not surge pricing, it's dynamic pricing, which is the exact same thing in case anyone wasn't sure. but yeah, it's an interesting user experience because even if you're buying flight tickets, like they have a new thing, or I guess not new anymore, but like you can lock a price down for 10 minutes, and that happens with different things you want to buy. You can like put in your cart and you can hold it for just 10 minutes, and they don't guarantee not changing the price after that. So it's definitely a kind of a balance between getting the most optimal price for your profit margins and sales volumes, but also having a good user experience to make sure you have goodwill with people buying your stuff.
Okay, so I see what I'm hearing is that so like Suchi and like Andre and several other people think that is usually like you don't want to change the end of the feet, but like there's certain situations you're okay with it. But I still think like the cultural norm as well, right? And people are more and more accepting of the fact that like prices can change in real time. And I think that I wonder is like this search pricing with Uber and Lyft does have moved people toward that directions. So okay, but in general, like also like not just like what technology can do, but also limited by human resources. Like when you install where you don't have employees going around the change like in real time, right? So I think we would say this like maybe we can just make some assumptions here. Just like maybe it sounds like daily would be like a reasonable assumptions for this task. So like we don't need streaming, right? Like every day we just have the price, the sales number, we also need the inventory, and then another aspect we have to talk about like competitors. So when you think of pricing, think like supply demand and competitors. So we need to know if we have a store next door, then we need to think about like what are they putting the price to be, because we really don't care about like competing like one-on-one on pricing on every item, but so it's pricing, there's so many key items when the prices we use to like benchmark like how expensive a store is, something item like eggs, milk. So we pretty care more to make sure that we don't appear more expensive than the neighboring grocery. Okay, so like that's how I think the discussion can go. So I'm gonna show a few more of the use cases, and what we want us to do is for each group, you can just pick like 1 or 2 use cases and talk about like what type of data we need for this use case, how fresh do we want the data to be, and based on that we can determine whether do we need like streaming data or like any other use case. Are we good with that? So here are the questions. Let me try to share the screen again. Cool. So I'm gonna start with the breakout. Can you see the questions? So we already done this in store pricing already, so we can talk about like transaction growth predictions, churn predictions, with online price optimizations, which may be like a little bit different, actually very different from in store. And we have a newer use case, the Gen AI use case, like customer support chatbots. So yesterday, I'm not sure if you shared on the chat, when Confluence has a very interesting case study on like customer 360, where they try like sometime when we have customer support chatbot, right? Like if I just place an order and they want to ask like about my order, then the chatbot also need to access information fast. So I feel like it's giving away some of the discussion answer, but hopefully you can get starting point for what you think about. How do I break out room now? And so I other questions, I think it's in the chat, like how I can change the way we store and discover data. So we're talking about like how unstructured data is optimized for write, right? You can just like write very quickly, you don't need to process data. The structured data is like optimized for read. That was in the past, but in the past our search has been the exact match. But AI makes it a lot easier to discover. So let's think about like how AI can help us change the way we store and like discover data. So one is a use case, so I was looking into a lot of use cases for generative AI, and one use case I think is like data organizations, like knowledge discovery for organizations. And AI is genetically very helpful with that. So I think another topic that I saw the group brought up is the vector databases. So one thing about like, so we see a lot of vector databases, but like do we need specialized vector databases? Or can existing databases like store embedding and just add the vector search on top of it? And like it can we or can we not, and what would be the limitations of like each approach? And also another topic I think would be very interesting because I found like data science today like really heavily still use pandas, and it's sometimes surprising me because like even like pandas creator thinks that pandas is not ideal, and he's gone on and create like as a tool like Apache Arrow and like Ibis, which is like more like neutral API. So we are hosting a talk with Wes McKinney, pandas creators, in like 2 months to talk about this. But I was wondering like why pandas is still popular and like what people get out of pandas. Also another like the last question is more to think about why stream processing is hard. So like a lot of algorithms, a lot of things that are extremely easy to do in batch. First of all, if you have an array of like values, you can get a median very quickly. But if imagine have an array of data that does not fit into memory, then how do we get like continually compute the medians with every incoming? So there's just one example. I just think a lot of things is like easier to do in batch, but really hard in streaming. And that's why people say there's a certain entry barrier to do streaming well. Cool. So I'm gonna start the breakout room now, and people can just assign themselves to the room. Yeah, please do pick your room. So I'm gonna screenshot the questions to Discord.
Wait, nothing is no group information.
Okay, join room 5. Let me move here. Hey.
Thanks everyone for joining. Good morning, everyone. We are group 2. We are ML Oppers, and we are presenting on chapter 4. So we are just going to introduce ourselves. Can you move to the next slide, please? Yeah. So I'm Raksha. I'm a graduate student at University of Michigan. So here are my teammates.
Hey, I'm Sebastian, machine learning engineer at Dataloop. And I'm Alessa with Software Engineer at Gap.
Yep. So we are going to begin the chapter 4. I'm going to talk about sampling and labeling methods that is mentioned in the chapter. So in the previous chapter, we saw how do we handle data in a system perspective. Now we are going to see how we are going to manage the data on a data science perspective. So to get into introduction to sampling in machine learning, let's understand what sampling is. So sampling in machine learning, it refers to getting a subset of data from the large data set. So that subset is called as sample. And real life analogy to give, when we go to a store to buy a fruit, we usually taste the piece of the fruit and then make a decision whether it is sweet or not. And when we make a decision whether to buy an entire lot of fruit or not. So in a similar fashion, even in machine learning, in many cases, when we don't have access to the entire real world data, we choose a subset. That subset is called as sample. And there are different techniques, methods of getting that subset from the large data set that we are going to talk in this chapter in machine learning. And this chapter gives a detailed explanation about how we can use these sampling methods to create our training data. So can you go to the next slide? So when talking about now we've seen the definition of sampling, let's understand why sampling is necessary. So when we are dealing with training the models, the first thing we need is data, and we often see that either we have access to all the data that exists in the real world, we might not have necessary resources to store it, we have memory issues, or due to health, privacy risk, like in healthcare, we might not have access to the real world data, so we'll have to consider a subset of data, or we might have a subset of data that we want to test on a new model. We just want to experiment how it works with our subset of data, and we want to quickly experiment and see how it's performing. So due to all these reasons, sampling becomes necessary before training the data. So there are types of sampling that is mentioned. We go by non-probability sampling and random sampling. So a detailed explanation is given about the types of, and there are different methods that comes into non-probability sampling and random sampling. We'll go one by one. So first we'll start with non-probability sampling. So as the name suggests, non-probability sampling, we are not using any probability techniques or methods to sample our data from a large data set. Instead, we are going to use some criteria, some information that we know, based on which we are going to select our subset to get our training data. So the different methods that are mentioned are convenience sampling, snowball sampling, judgment, and quota-based sampling. So convenience sampling, samples are selected based on availability. For example, in Twitter accounts, if we have in Twitter accounts, suppose if we are going to scrape the data based on hashtags, which is readily available and it is very easy and it is very speed that you can get, like suppose if you have launched a new product, so hashtag new product, you can extract or scrape the data based on that hashtag, which is very fast and there is no probability technique that requires here. So then comes a snowball sampling, like for the same example, like scraping Twitter accounts, you select a legitimate Twitter account from which you start scraping data, then you go on like where the person follows and then you go on sampling their data. So this is an example for snowball sampling. So judgment sampling is like you are domain expert for certain use case, you already know what kind of subset is required or a sample is required. Based on that, you kind of do a judgment sampling. Then comes the quota sampling, where samples are based on predefined quotas without randomization. Like you are, an example is survey response, like you already have a predefined problem statement, like I want 100 responses from a group of people, even without knowing the original distribution, like you are having a predefined problem statement, like I require 100 responses from different age groups. So that is what is an example for quota sampling. This non-probability sampling does have some limitation because when we are sampling based on certain criteria, we cannot generalize it to the real world entire data. It might be a biased data, especially when you're just selecting only few based on certain criteria. So definitely your data is going to be biased, and it is completely.
So we can move on from this because for a simple let's use machine learning.
Yeah, we can move on to the next. So there are many examples that are mentioned for non-probability sampling, especially for language modeling. The data is available like Wikipedia, Reddit, so you can collect the data and start using it for your use case. There is sentiment data analysis use case where you can get data available, like it's in a convenience method, like IMDb and Amazon reviews. So you can get reviews of people who have given reviews. It might be biased, but you will get some data. And example would be self-driving cars. The data collection focuses on the areas with favorable conditions. Like you might have a lot of data where there is a sunny. Weather, for example, Bay Area and Arizona, and you might not have much data that locations where there is no or rainy conditions. Next. So we have seen the non-probability samples based on criteria and their limitations. The other type of sampling is random sampling method. So when we're talking about random sampling method, there are certain types that are methods that are mentioned in the chapter. Simple random sampling, stratified, weighted, reservoir, and importance. So simple random is based on like simple random. The name itself suggests like we are going to give equal probability for an entire distribution, like 10% of each class we are going to take and we are going to sample. That is one way of doing the simple random. sampling. So you can randomly select 10% of the population, giving all the members of the population equal 10% chance of being selected. So there is a drawback in this method, is that it is very difficult to get the rare categories of data that might not appear in your selection. So to overcome this drawback, we have stratified sampling, where you can, before dividing or before doing the sampling, you can initially divide your population into groups that you care about. Then you can sample from each of this separately. So when you're going to divide initially the samples, there might be a drawback, like in case of multi-label task, it's impossible for us to divide all the samples in groups.
Yeah, I think it works. Okay, perfect. Awesome. Yeah, we're good. We're live.
Awesome. Cool. Yeah, I'll just give everybody just maybe a couple seconds before we kick this off. But yeah, happy Saturday, everybody. Thanks for tuning in on YouTube or on Discord. Easy.
Ready? Cool. So let's get started. Yeah. So hello again, everyone. This is report cricket. I'll be back with an explanation of the name in a minute. So today we're presenting chapter 6 of the book, and yeah, so we are actually a merged version of two different groups, and both of our former groups are rather quiet, so we decided to call ourselves Speed Crickets. I'm Suchi. You have seen me last week as part of the host team. And this week I'm presenting for the chapter. I'm most recently at Meta, previously been at a couple of different hardware and software roles, also associated with Georgia Tech. Let me pass this on to Sharma, who is also on our team.
Yeah.
Yeah, I guess you can hear me. Yeah. So I'm Sharma. I've been working in the industry for a while. I work at Amazon right now, and yeah, I've been doing machine learning stuff. Yeah, that's about it.
My name is Charles. I'm an ML Barely, also known as Google Life Sciences. Been working on developing ML models, infrastructure, and most recently working on applied large language model research. Been working here for about 5 years. And that's
cool. Yeah, that's all the presenters today. We do have a couple more group members who aren't joining today, I believe. So can you move on to the next slide? Cool. So we'll start with the chapter summary. Just start with TLDR. So the next thing is this is the fun part of ML. This chapter deals with ML model selection, which is sort of the part of ML, right? So the chapter will go on to talk about how to select models for your task, different aspects of model development, including ensembling, and also talking about tracking version experiments, a little bit about distributed training, and finally about how to evaluate models. We have added a couple of key takeaways here. This is more of a personal takeaway from our team. What we found interesting about this chapter. So the first thing we realized is that models are like code, and they need to be evaluated in the context of the theory and the business domain. And this is a recurring theme in the chapter, but also in the book. Similarly, models at scale require a different set of skills to train and manage compared to compared to a small model. This we thought has parallels in databases. We also noticed that engineering leadership might need to understand how scaling works, like they typically do for backend systems. For the last part, one of the interesting things we noted was model testing includes an online and offline component. So offline eval is not a substitute for online performance, so you do need to do both. So we thought those were the highlights for the chapter. Can we move on to the next slide? We will be diving deep into each of these aspects going forward. So the first part of the chapter was model development and training, and the second part was eval. So let me start with evaluating ML models. So the idea of evaluating ML models is given an ML task, what model should be used for it. Obviously, given unlimited time and energy, you will eventually find the optimal solution, but that's not the point here. The point here is that in production, there's always a cost associated with developing the model, and so the idea, and as we know in industry, all model solving a business problem have the same constraint they were doing yesterday. So yeah, and in the chapter section goes on to talk about how current ML is split into neural networks versus classical ML. The classical ML still stays relevant for many problems, and knowledge of common ML tasks is essential to actually go about evaluating which model is ideal for your task. Next slide. So a couple of different things to consider while evaluating the trade-offs. In real life, other than model performance, you might want to think about explainability, resources, like in terms of compute, cost, memory, and so forth. And also remember that depending on which model you use, you're looking at differences in many different aspects, right? From data collection process to deployment to training pipeline to everything. So we do have an example here that sometimes you might have a model that has a lower accuracy, but it needs, if it's faster to train, it's interpretable, and easier to deploy, maybe that's your preferred model in that situation. Moving on to the next slide. So check out these really cool tips for model selection. The first tip was avoid the state-of-the-art trap, which is basically, state-of-the-art means that the model performs better on some static datasets, but in production or in your specific use case that may not apply. The second and super valuable tip is start with the simplest models because they're easier to deploy, debug, and at first they provide a baseline for evaluating your complex model. Avoid human biases, and it should go without saying. Evaluate good performance now versus good performance later, which also is a pretty valuable idea in that you want to account for potential future improvements and validate that improvements are even possible, but you do want good performance now. And as always, you have to evaluate your trade-offs. It might be the trade-off between false positives and false negatives. It might be compute versus accuracy trade-offs and so forth. And the last but not the least is understand your model's assumptions. The theoretical assumptions of your model and see whether your data satisfies them. Can we move on to the next slide? So while we were going through this section, we thought that this had parallels with general software engineering. For instance, the first principle, don't use something just because Google did it, right? In software, you would typically say don't use the latest framework just because Google did it. In ML, you would say don't use the latest model just because Google published a paper using it. And similarly, for establishing a baseline, in software, you typically start with the POC first, and in ML, similarly, you should ideally start with a simple model first. For the third point, don't by shed something from experience or preference. This is the human biases part of it. We tend to do this for frameworks or languages in software. It's the same with ML. When you're choosing a model architecture, you should ideally not just go from experience or preference, but look at the specific problem and what it requires. Can we move on to the next slide? Next slide, please. I think we went one too far. Sorry. That's one. There you go. Deploying the best now versus optimizing for later. Obviously, in software, we tend to deploy the best code now rather than optimizing for later. It's the same with models. Trade-offs, of course, that's true for software as well. Is this feature something that will change later? How many boxes do we need? Things like that. Versus in ML, it's like, do we care more about false positives or false negatives? Does this application need a GPU? Things like that. For assumptions, in software, we tend to say understand your tools well before you commit to them. And with ML, it's the same thing. Understand your model well and the assumptions and the theoretical assumptions before you commit to it. Next slide. With that, we'll have a quick poll started about your experiences in choosing model. We just want to get a sense of which models tend to be most used in industry versus academia by different people. So that's the poll going on. And while that's up, I will be talking about a case study. Just a second so that okay. Cool. So this case study is from my work. So this was a particular situation where we were trying to predict relationships between users in the network, and this is essentially a classic use case for a graph neural network. When you're thinking of users in a social network and you are trying to predict relationships between them, this is literally like a textbook example for graph neural networks. So obviously the original implementation followed that theoretical example, and they implemented a GNN. It had very high precision, which was the priority in this case, and essentially the model was doing really well. And it went on for a while. After about a year or so, we were trying to do exploratory studies to improve the model performance, and that's when we found a couple of interesting things. So the first interesting thing we found was that we could replace a good amount of the predictions with just very simple rules. So we could just use basic heuristics, and that was giving us pretty good predictions for a good chunk of the cases. And the second thing we found was XGBoost would cover majority of the remaining cases that weren't covered by the rule, and obviously that uses much fewer resources than training a graph, training a GNN with all of the node features and edge features and all the jazz. So this led to a couple of interesting lessons for us, for my team, and for me personally. That sometimes even when your problem is a textbook example use case for a model type, your specific situation may not need it, and this can happen for different reasons. It might be that your data is simply much simpler than needed, or maybe it's much richer and it already has it has enough information to be able to use a simpler solution. And the other interesting thing might be that your metric requirements and resource requirements might simply be different, right? So you may not need as complex a model to get the results that you are looking for. The other lessons from this were always revisit your model architecture choices and see if it still makes sense. In this case, we did have a model that was run pretty successfully, but one thing we noticed was as the user graph changes, VNNs require retraining, and that's not always feasible at the frequency at which it is required. So it's a good idea to always revisit your model architecture, see if those choices still make sense, and kind of loop back to that. The other thing, and this I know the other lessons also mentioned in this chapter, but this one particularly stood out to me, is that establishing baselines is really invaluable. In this case, it turns out that knowing that XGBoost or even simple rule-based predictions can be useful, that tells us a lot, and we should be using baselines like that to evaluate our model choices. So that's a case study from me, and I'm going to pass down to Sharma, who will continue the discussion for this chapter.
Hey, thanks, Satish. So I guess now we get to the part of the book that's a little bit more academic and has some theory behind it. So a couple of things that the book talks about in terms of giving, I guess, a reader a sense of what types of models exist. One of them is ensembling. I think this is a fairly standard textbook process, but from an industry point of view, I think it's useful to understand the higher level idea here. Typically, you deploy a linear model as a first case just to see what the data set is like and what the performances are, and then you move on to a slightly more complex model. Usually today, people jump to DNNs or maybe DNNs is the second thing, but there's a lot of value in these ideas of bagging, boosting, and stacking. And all three of them sort of combine the basic principle that your data is pretty rich and it can be trained for far fewer resources to get very good performance. So with bagging, the general idea is to create different sets of the same data, assume an independence on them, or rather between them, and train multiple models off of them, and then use that combination to give you an aggregate performance. This model is fairly fast to run because it's it's more or less just plain code. Typically, people use run forest, which are just efficiently learning processes, and these are really fast to run. But the con is they can be great in performance simply because they're sort of like overfitting because they try to understand different pieces of the data. And when you go through unsupervised methods, you might understand better relationships within the data. And this is just one approach that you might want to think about. Boosting is another classical ML technique where you train a series of models, and each subsequent model that you train is weighing the data on which your previous models did not work well on, and giving those models, those weights, a higher preference. So that way, the samples on which your model did not perform well is also scrutinized a bit more. And this boosting technique is something that is very popular, and it's part of a very popular package for XGBoost. If you go to Kaggle or other kinds of platforms and other case studies, XGBoost is predominantly used simply because it's just easier to intuitively understand where the performance gains are. And a little more of a complex technique is stacking, where you have possibly different models, and you try to combine them in some way, which you then use as a meta learning process. So all three of these techniques are a little bit rooted in the theory, and the book, for obvious reasons, doesn't cover them too much, but it's fairly useful to get a sense of these ideas. So if you are somebody who's evaluating these techniques, you please know that they exist. But you do have to go into a little bit of theory, for example, to understand why stacking works, and or how to combine them, how to have some stability over the outputs. Next slide, please. Okay, so like the theme of developing software, tracking and versioning of your experiments is pretty important. So with code, given the deterministic nature, you typically use something like Git, and you kind of know that between Git commits, your code is changed, this is how the performance changes, and those types of sort of metrics can be teased out. But with models, it's a little bit different because you're not only tracking the code that's powering the model, you're also dealing with the entire data set. So it's important to understand what data you use to first check your baseline, and then make sure that those artifacts are reproducible, and make sure that you track those performances across training runs. Typically, an ML engineer or research scientist will more or less pick up a bunch of data, put them in a S3 bucket, something like that, and then use additional tools. So one of them I think in the book was weights and biases attention, and that's pretty popular across the board these days. So you use that to kind of train your model, make sure that you have a copy of the metrics, then you kind of do the process over and try to understand what's happening. The book mentions a few things which are valid to track. So loss curves, for example, give you a good sense of how much the model is learning. You can kind of understand the gradient of this graph to get a sense that things are going well. Occasionally, you'll see something weird, and then you have to go backtrack. And of course, there are other similar ideas like just understanding the performance metrics across. If you have classification, if you have accuracy metrics, and things like that. And versioning also has a small problem when you're dealing with a lot of data. You don't have a lot of standard tools to use. I think typically these days you have FS packages, so basically the file system replacements that can use Git to understand that a large binary blob has tiny changes within it, and then you can track them. So data versioning, I think, is an evolving process. Code versioning, I mean, the entire conversation started like basically a decade or two ago. Data versioning is just kind of getting into the picture that we should do this. I think if you go to like Hugging Face or other repositories today, you can kind of see them doing that with the model artifacts where you have these massive neural networks and you have to kind of version. Right, next slide, please. Okay, and then the other practical consideration for developing models is how you debug them. So given that with respect to software engineering, software testing is a fairly established standard, and most people know how to do it, ML models are similar, but they're also different because you still have to understand how the theory works to get a sense of what breaks down. So on the theory side, I think you have to deal with you have to really go past the subject matter expert. But if you're just looking at it from a software side, there are simple ideas that you can try as a practitioner, right? So for example, one of the things the book talks about is how you overfit on a single batch. So this one is kind of interesting because you know that model is supposed to overfit if you kind of give it all the data and you can cheat a little bit. So if you're not able to do that, basically if you're not able to cheat, then you know something is off with the implementation or the data or your code, something like that. So typically when you write a unit test, you say that you're given a single parameter software. That's kind of similar to what overfitting on single batches. And then you have simple ideas like making sure these are random seed, right? So simple things like you run this code, you hit the run button several times, and you roll out, you should get the same output. So just making sure that these basic ideas is things that you can try from a software perspective. And I think you have to like kind of understand how much you can do that on the software side, and then how much you have to really understand other assumptions of the data, how much you have to do like data analysis to see if this data is good for like a model you kind of thing. So in terms of challenges, the really interesting thing is that ML models, if they're kind of in an in-between zone where you don't know how to interpret them well, or if they're not easy to interpret, they might fail silently, and you will never understand this until you see dramatic differences in your business software. Like if you're tracking business metrics, like something even as simple as revenue, if you deploy a model that's going to affect it, there's a good chance that you will not see that until after a subsequent amount of losses has been sort of taken on. And given that ML models typically use data that is cross-cutting across the entire organization, you really have to understand every team's sort of like development process, what kind of culture they have. If you're working with a company, you're culture and those sorts of things, like how they deal with updates to the training patterns and things like that. Next slide, please. Okay, and I think in the book we have a couple of points about, and I'll just start to the slide. So in the book, in terms of data training, we have like a couple of pieces. One is data and model, data parallelism, the other is model parallelism. So data, you're sharding your data on multiple machines and training them and having some sort of synchronization process between them. And for model parallelism, your model is spread across multiple computers, and you kind of train them in that distributed fashion. I'll kind of skip over these details because you have to go and understand like the papers to see what people have done. But there are different ways to kind of implement distributed training. Next slide, please. Yeah, and this is a case study that's probably from my work from a while ago. In the interest of time, I'll just run through this. So there are two main lessons here. One is baselining. The other one is making sure that you pick the relevant metrics. In terms of baselining, before you jump to a complex model, you should try to pick a smaller model. Make sure you're tuning that a little bit at least to see if you can get good performance. And then in terms of trade-offs, something as practical as the memory cost to load this model and keep it in memory, if you have a bigger model in a bigger box, you can use that as one of your metrics if cost is consideration. So you can kind of take that, plot that and then see if choosing a smaller memory footprint does not affect your final outcome. So if that's the case, then you have choices to make. Yeah, next slide, please. And I think I'll hand it off to Charles.
Yeah, talking about AutoML. So AutoML aims to automate the process of finding ML algorithms to solve real-world problems. There are two classes of AutoML. One is a soft AutoML, and another is hard AutoML. Soft AutoML is the most popular form. But its most popular form is hyperparameter tuning. The goal is to find the optimal set of hyperparameter in the search space, and the popular method is random search, grid search, Bayesian optimization. You would input your training data and get a model output with this like black box kind of training thing. With hard AutoML, it's what if we treat the model components or entire model as a hyperparameter. It's also known as architecture search or NAS. The challenges with hard AutoML is that the optimizers are sensitive to hyperparameter hyperparameter settings, and the solution is learn optimizers. They can train on the same data set as the neural networks and train ones on a set of existing tasks that generalize it. The phase of model development typically starts with like before ML. You try out heuristic, simple non-ML solutions, and then you want to iterate on the process. First, starting with a simple ML model architecture, like logistic regression, gradient boost, and optimizing the simple ML models. And the reason to do that is because if you pull a complex off-the-shelf ML models, it will be difficult to iterate on the ML models and improve the accuracy. Like if you have a complex model that's already 90% accuracy, and you try to boost it up to 98% or 95%, that kind of small model boost would be difficult if you have a complex architecture at the beginning of it. And optimizing simple models, we can optimize either the objective functions, hyperparameters, features, and then we go with a complex model, try a more complex architecture, and repeat step 2 and 3. Next time, I'm talking about offline evaluations. So when we start with model evaluation, we want to start with a baseline. We want to translate the model matrix to usefulness and there's a need to establish a baseline first, because without baseline, you cannot compare apple to apple. You can test your ML model against another model that generates output at random. For example, the book gives an interesting example where MLE achieved a 0.9 F1 score, but upon closer inspection, it seems that the task that he's solving has 90% positive class. So if his model just randomly output the positive class 90% of the time, the F1 score will be 0.9 anyway. And then another way is to represent simple heuristics for the other business problem in mind. For example, like decision tree, zero rule, or just based on plain observations. And the third one is like human evaluation. So I'll be going, I'm sorry, let me skip back. I'll talk a bit about what we do at my team. In my team, one approach that we often utilize for establishing a baseline is to pull off-the-shelf model without any fine-tuning and evaluate its performance as is on the task in hand. Another way we can do this is using AutoML with the input that you already have, and use that, evaluate the performance of the AutoML as the baseline of the model. Next, I'll be talking about evaluation methods. There are multiple methods that we can use to evaluate ML models, and it's critical that we have this in place in the CI/CD pipeline so that we are able to iterate on the ML models and improve on it. If you don't have something that you can measure, you cannot improve on it. So the first way we can do this is perturbation test, and how we do that is we add noise to the dataset and test the model performance. In my team, we have this critical view of safety machine learning models, which is you are trying to predict the golden triangle in the gallbladder. Like, in order to achieve that, there are 3 requirements that you need to meet. One is only 2 structures can be clearly seen connected to the gallbladder, and the lower 1/3 of the gallbladder is separated from the liver to expose the cystic plate, and the hepatocystic triangle must be completely clear of tissue, allowing proper visibility. And our research scientists hand us the ML model to productionize it, but during testing of the ML models before productionizing, I noticed that when I rotate or crop the dataset, the performance of the model fluctuates a lot. And that's proven issue. And then another way we can do evaluation is invariance test, which is you perturb some of the features in the dataset, and with the domain knowledge that you are not expecting any changes in the output with this perturbation. And another way is directional expectation test, which dive into invariance test. Certain changes to input should cause predictable changes in outputs. So back to the critical view of safety. When I was applying black patches to the images, I noticed that the model is only looking for gallbladder instead of the 3 criteria that I was mentioning just now. So that's something probably problematic, especially you don't want to deploy a model like this in healthcare. So this is yet another example that evaluation method is really important in production. And then the next one is about model calibration. The idea is to compute the probability that given a label, label equals to 1 given the model probability. If the predicting model says there will be 1,000 clicks in production, if it's 900 clicks, then it's not probably calibrated. And then there's like 2 more methods about prediction confidence, which you can evaluate via softmax and also slice-based evaluation. The book talks about Simpson paradox, and that there are like 3 approaches to that. One is heuristics, error analysis, and also slice finder. I won't be covering that in detail over here. I want to talk about how things go in the age of Gen AI. So evaluation of LLM can be categorized into 3 major groups. One is knowledge and capability evaluation. I won't be focusing in this slide because I have 2 other slides that covers that. The second approach is alignment evaluation. Why do we do alignment? The trained objective LLM, which performs the next word of prediction or determine whether 2 sentences are contextually related, are not necessarily in line with human values. LLM may generate undesirable content like biased, toxic, privacy sensitive biased content. and also unfaithful content, like fabricated contents, misinformation, hallucinations. Unfaithful contents like this, it affects the trustworthiness, but also application in professional fields like healthcare and law. And how do we evaluate for this alignment is through reinforcement learning from human feedback, PPO, DPO, and KTO. I will talk at high level about this PPO, DPO, and KTO, but you can click on these links to learn more about it. So PPO aims to maximize the expected reward while preserving large policy updates, and it takes in input states and rewards from the environment, and it outputs actions to be taken in the environment. Whereas DPO, it optimizes policy based on human preference using a binary classification of objective. So over here, I provide this example from worst completion and better completion. That's the input that it's taking from the environment and also human preference feedback. The output is the actions to be taken in the environment aligned with the human preference. KTO is yet another approach that comes out by Stanford. It aligns model by maximizing the utility of LLM generation based on prospect theory without requiring detailed preference pair. It takes the input of LLM outputs with binary labels indicating desirable or undesirable outcome. And the output is LLM generations aligned with simplified human utility functions. KTO, it's more generally used because of its ease of input, like more user-friendly input. And the third part of evaluation for LLM is safety evaluation, and that's robustness against adversarial prompts. So the adversarial prompts crafted to mimic plausible user errors like typos or synonyms. It aims to evaluate how slight deviations can affect LLM outcomes while maintaining the semantic integrity. These prompts are then employed in diverse attacks, including sentiment analysis. In diverse tasks, including sentiment analysis, NLP, natural language inference, reading, comprehension, machine translation, and math problem solving. There's a case where DeepMind it figured out that if you repeat the word poem like 1,000 times, then ChatGPT will start spitting out training data. That was like early this year, and the issue has since been fixed. So when developing LLM, we need to do it carefully in the pillar of these three groups. So I'll be talking about the first part which I skipped just now, evaluation for LLM. There's a difference between evaluation for LLM versus the system itself. Large language model out of the box, it performs various tasks such as chatbot, natural entity recognition, text generation, summarization, Q&A, sentiment analysis, and translation. And there are a bunch of standardized benchmarks that's like this ground truth dataset. And this becomes tricky because getting this ground truth dataset on a wide diverse range of tasks is expensive. There are a few ways to perform offline evaluation. One is through eyeballing, and this is mostly employed when you are doing like chain of thought prompting and you want to just quickly evaluate your prompt quality. There's also utilized a powerful large language model like GPT-4 to generate the meaningful synthetic evaluation datasets, and this usually requires human in the loop. There's also large language model guided evaluation, which is essentially using LLM to evaluate LLM. And how you do that is that you ask LLM to produce output. You get the LLM to score the output of these results, and that also requires human in the loop as well. There are a bunch of existing frameworks that supports this. There's OpenAI Evals, Vertex AI Studio, Language Model Evaluation Harness, Uptrain, PromPatch. All right, I will hand it over to Suchi to talk about the discussion questions.
Sorry, yeah, I think Sharma is supposed to go over there.
Oh, yeah. So in terms of discussion, it seems like most of the chapters about baselining and understanding how your models work. So here's a couple of topics to think about. So for LLMs, we have human eval. So that might be something interesting to understand. Most people without models on leaderboards, so you could probably talk about that. And AutoML was interesting because it was a big deal a while ago. But now with a lot of these neural network frameworks, how do they fit into your work? And in terms of your own personal work experience, if you have model architectures to talk about, maybe you can go over the trade-offs and the choices you make.
All right, hey, Saket, can you hear me?
Yes, Len, I can hear you.
Okay, great. So then we'll just proceed as planned. the presentation as we discussed.
Sounds great. Sounds great.
All right, thanks. All right, just meeting the last few people into the room. Yeah, sorry. Wait 30 more seconds because currently I'm trying to online versus edge, model progression, and trade-offs between ML and the cloud and the edge. Glad you all could step around to this point to make an introduction. Sakit?
Yes. Hi everyone. Very happy to present today. I'm Sakit. I'm currently a master's in electrical engineering student from UCLA. Right? And I hope to give some of my insights gained throughout past couple of years and hopefully have time for some good discussion. Back to one.
All right, thanks, Sakit. So because we lack manpower, I resorted to a Gen AI presentation application called Gamma to help generate these slides. So about 70% of this content presented here is AI generated. Most of the layouts, images, and quite a bit of the descriptive text. So some of the slides were overly verbose, and I tweaked some of the responses and manually added a few slides. But speaking as a former product manager that did customer-facing presentations, I can kind of get why Elon says AI will take all our jobs. So this chapter starts with 4 ML deployment myths. The first myth, you only deploy a few models of production. In reality, there could be hundreds or even thousands of models. Here's an oversimplified hypothetical example with Uber. Say it is operating in 20 countries, each with 10 models to account for different regions, user profiles, etc. That's already 200 models right there. According to the book, Uber actually has thousands of models in production. Second myth, if you don't do anything, the model performance remains the same. We all know that the performance of any software system degrades over time. So with ML systems, the distribution shift of training to production is an additional factor to account for. The third myth, this is closely related to the second myth. You don't need to update the models frequently. So actually, you do, because the ML system performance will degrade otherwise. For example, Weibo and TikTok updates their models once every 10 minutes or so. The fourth myth, ML engineers don't need to worry about scale. It seems like only a few big tech companies with massive user bases only need to worry about that. However, as a collective, they employ a majority of the ML workforce. And if you're working in ML, you need to understand how to scale your application in terms of data and users, since big data is one of the big enablers for this recent ML renaissance. So batch prediction versus online prediction. How does your ML system generate and store predictions to users? So the book is quite pedantic about there being 3 modes of prediction. The first is batch prediction is when predictions are generated periodically or when triggered. This mode uses only batch features, which is features that are collected periodically, stored in databases or data warehouses. Number 2, one form of online prediction is when predictions are generated and returned real time, but it uses batch features. The other form of online prediction is when it uses both batch and streaming features, and particularly in this case, if it uses streaming features from real-time transports, this is also known as streaming prediction. There are use cases where batch and online predictions are used in the same ML system, which requires unifying or integrating 2 pipelines in some way. So what are the pros and cons of batch prediction? Batch predictions are good when generating a lot of predictions, but don't need to store all the results immediately. This can leverage distributed computing for high volume processing of samples, which in turn can be used as a trick to reduce the perceived inference latency since you're just retrieving pre-computed results. The problem with batch prediction is that it makes the model less responsive to user changing preferences. For example, a Netflix user could be sick of binging one genre and immediately wants to switch to another. Also, it's not good for use cases where the user needs immediate response, like language translation. Online prediction is better for that use case. What are the pros and cons of online prediction? As I just mentioned, online prediction is tailor-made for use cases that require real-time responsiveness. Similarly, it is easier to process that using online prediction because you immediately get feedback and can iterate quickly to improve the model. However, the problem with online prediction is that it takes significant computing power and infrastructure to do it in real time at scale and at a low enough latency that is acceptable to users. Also, this added complexity in real-time transport infrastructure means that service disruptions or system failures are more likely to happen here than in batch prediction. So what happens in a system that combines both data types for batch and online predictions? To leverage the strengths of both batch and online prediction, a unified pipeline can be established. This approach combines the efficiency of batch processing with responsiveness of real-time data handling, creating a flexible and scalable solution for diverse machine learning deployments. Sounds easy enough, right? Yeah, it's too easy. So the previous slide was kind of a dumb slide. It was an untouched AI-generated platitude, which completely ignores the challenge in implementing this hybrid system. The book emphasizes that this is difficult in practice because the two different pipelines can easily cause bugs in production. Many times, one change in the pipeline isn't directly replicated in the other, resulting in the system extracting two different sets of features. Why? Because sometimes different teams work on each pipeline without close collaboration. So sometimes just having a streaming pipeline by itself isn't fast enough to generate predictions for the user. Now what? You can do three things to improve speed. 1, make the new hardware to run the model faster. 2, make the inference faster, aka inference optimization. And 3, make the model smaller, aka model compression. 4 ways of which we covered in the following slides. The first method discussed in the book is low-rank optimization. This involves replacing high-dimensional tensors with lower-dimensional tensors to reduce the number of parameters, resulting in reduced model size and faster inference. One type is compact convolutional filters using industry recognition, like SqueezeNets, replacing 3x3 convolution with 1x1, achieving the AliceNet level accuracy with 50 times fewer parameters. The issue with this method is that it is specific to certain types of models, like for convolutional neural networks, and not widely applicable to many use cases. The second method is knowledge distillation. This is a model compression technique that uses a large accurate teacher model to train a smaller student model. One example of a student model trained by a teacher model is Dilbert, which reduces the size of the teacher BERT model by 40% while retaining 97% of language understanding and 60% faster inference. So one interesting advantage of this method is that you can have two different architectures for the teacher and students. However, a big disadvantage is that it is highly dependent on the availability of the teacher model. The third method is pruning. The book makes a distinction between two types of pruning. The first, more common one, is weight-based pruning, which is set to set less important parameters to zero while leaving the network architecture intact. This makes the network more sparse, which requires less storage and dense architectures. This is easier to do without hurting the accuracy of the model than the second type of pruning, node-based pruning. Node-based pruning is removing entire nodes of the neural network, changing the architecture and reducing the number of parameters. This is more compact, but it is harder to do without hurting accuracy. And a big disadvantage of pruning is that it introduces biases into the model. The fourth and last method discussed in the book is quantization. This is the most general and commonly used model compression method, which generalizes across many architectures. Quantization reduces the precision of the neural net's weights. For example, converting them from floating point to integers. By using fewer bits to represent the parameters, you can reduce the memory footprint and improve computation speed by reducing training time and inference latency. The disadvantage to quantization includes rounding errors, which can lead to big performance changes. Now, there are two motivations for model compression. The first, as discussed previously, was to make ML models run faster. The second is to make models small enough to be able to run in edge devices, whose performance is constrained by slower processors and smaller memory storage. Now, why do you want to run ML models in these small edge devices rather than cloud? Do you like money? Or rather, do you like to save tons of money? So let's go over the pros and cons of ML in the cloud versus the edge. So you can choose to run ML models either on the cloud or edge devices. If you choose cloud, these managed cloud services like AWS, GCP, Azure make it easy for you to get your model deployed and scale up and down according to demand. However, a big downside of the cloud is the cost. For example, big organizations like Intuit and Pinterest spend hundreds of millions of dollars per year, and small to medium businesses spend in the range of tens of thousands to a few $1 million per year. If you're not careful with your deployment settings, you can kill your startup by leaving instances running in the background, just like a story in Hacker News. So instead of cloud, you can choose to run your model, or as much as you can, locally on edge devices. Doing this has several advantages. First and foremost, you can save money from little or no cloud compute. Second, you don't have to worry about network latency as much. And third, in terms of user privacy, you can avoid passing user info over the network. The problem with edge devices is that they're limited in power, both in terms of computational processing power and compute and battery power. So now Saket will go over new solutions for the problem of putting ML models, including transformers, on edge devices. Over to you, Saket.
So thank you, One. As one was mentioning, there are own set of problems for edge devices and cloud solutions. But I think over the few years, people have been looking at hybrid solutions and trying to actually understand what are the advantages and disadvantages and how can newer solutions account to them and things like that. So as he mentioned, I'd just like to reiterate a few points. That is, what are the problems with deploying ML models on the edge devices? So the main problem, as one already mentioned, is the limited power. Also, since these edge devices are tiny, there are good sets of problems associated to latency. Right? Although they're real time, let's say your ML model is big enough and it needs some time to actually do the inference, there are latency issues. And again, there's always a compromise between performance and this latency. That is, you can decrease the size of your model, you can prune your model, but at the same time, there's also some loss in accuracy or loss in performance associated with them. So how do people generally solve this? As one mentioned, that there are a number of techniques, model compression and that is quantization and things like that. And also, by design, people have tried to solve this in the past. MobileNets is one famous architecture that most of us have already come across or probably read about it. And again, there are newer techniques like sparsity distillation and other sets of techniques. But what's interesting in today's ML era is hybrid cloud edge solutions. That is, can you find out a way to integrate both cloud and edge together in some hybrid fashion so that you can take best of both worlds and try to account for disadvantages of one by the other? So how do people usually do it? So let's say you have a ton of processes and information and ton of data coming to your edge device. You selectively push not so important data to the cloud so that there's a bigger ML model on the cloud which can run the inference and keep the predictions ready. And whenever your task or whenever your application needs it, the edge device can pull those predictions from the cloud and just serve it to the user. So again, there are lots of limitations and lots of advantages. If latency and immediateness is a requirement, this is probably not a very good solution, but gets the job done if you have good amount of data coming in. Let's say you have a data that is, you have an edge device that is mounted to a vehicle, and let's say you want to train a machine learning model on this incoming data, but you don't necessarily have to serve the predictions as they come, right? So it's good to send the data that is coming to the edge device to the cloud, run a lot of algorithms, and then whenever you want, you can just deploy the model, serve the predictions through the edge device back again. Also, there are other newer solutions such as collaborative federated learning. Again, the main idea of federated learning comes from the fact that let's say a user does not want to share their data, but still wants their data to be a part of the training process of the machine learning model. So there's a big concern of privacy here. That is, you don't want the data to leave from your device, but how can you still do solutions by actually using cloud and then train models collaboratively? So this is again a notable framework and a notable method people use in current industry frameworks. Can I get the next slide? Thank you. So one important slide that I wanted to talk about was how do people usually, are focusing on deploying transformers on edge devices. This is a very important slide, I would say, because transformers today have essentially become the backbone of ML. I mean, everyone today wants to deploy transformers for their own kinds of applications, let it be just conventional NLP tasks or even a lot of vision-based tasks, right? So what's the problem with transformers? you all must already know that these transformers have these huge blocks of multi-head self-attention. So usually it's 8 plus or 10 plus heads of multi-head self-attentions in each transformer block. So all of these attention blocks have this calculation of dot product attention. That is, you have these key, query, and value sets, and you have to do dot products to see which keys associate good with a particular query vector, right? So these are too much computation, and I mean, essentially these are lots of matrix multiplications and are an overkill for on-device memory and battery support, right? So you'll have to keep in mind, can the edge device perform these kinds of activities or not? So how do people solve it? Existing solutions. I mean, some of which are also exciting and not so exciting are reducing the quadratic complexity to linear complexity. That is basically dot product attention. Can you try to linearize it? Can you bring down the complexity from O of n square to O of n? And I mean, this can be done by lots of ways. And also, can you see whether you can lower the precision? That is, let's say you are using floating point 32 and now you want to switch to floating point 16, or let's say integers, and delved into CUDA and how generally a GPU is constructed. You know that there are lots of limitations from the hardware side itself, which needs to be taken into account when you're actually designing them for ML applications. So these are, I mean, different techniques such as how do you place your CUDA cores, and let's say you have multi-core, multi-thread GPUs. How do you place them such that there's less data movement and higher latency and things like that. And also this paper also talks about how do you convert the calculations to
All right, so we are live. So thank you everybody from the book club, and also everybody that's streaming on YouTube, or wherever you're streaming it from on your phone or on your computer. This is the book club for designing machine learning systems, and we've been going through a chapter a week from Chip Klein's book on designing machine learning systems. So we're going to be discussing chapter 8, or should I say we have group 10 here that is presenting chapter 8, and that's on data distribution, shifts, and monitoring. So very exciting relevant topic for machine learning models and artificial intelligence. So I'm going to kick it off to Mo and Bashar from group 10 to present group 8, group 10 to present. Chapter 8. So, without further ado, kick it away, guys.
Nice. All right. Thank you guys very much. Thank you. Thank you for attending the book club meeting today. And we are group 10. Today we're going to present for the chapter 8. So please wait me when I share my screen. Okay, that's great. All right, so you guys can see my screen now, like the presentation. So, oh, great, perfect. All right, so thank you guys very much. So the chapter 8 is about the data distribution, shifts, and monitoring. So let's have a quick introduction. So we have basically 3 members on our team. The first member is Maria Oduo, but she's an independent researcher, but today she lost some business, so she couldn't attend the meeting. So today she lost some business, so she couldn't attend the meeting. So there will be 2 members today presenting the chapter. It's me, Mo. I'm from Japan, and I'm doing research assistant in NARA's Institute of Science and Technology. And also we have Babesha, which is he's doing the NFP engineering in Turkey.
Yes, hi there.
Yeah, it's great. Yeah. So, but before we proceed to the takeaway chapters, we have a question that we want to ask the participants today. Like,
so just a second, we're still setting up the poll. So we need a couple more minutes. But you can talk a little more about your research in the meantime.
Okay.
Yeah, sorry, we have.
Yeah. So for me, I'm doing like kind of research about speech processing. Like I'm focusing on the unsupervised or self-supervised training patterns. Like I'm trying to train the models to learn some vector embeddings for the sounds for the speech. Like the model can have the ability to distinguish the segments or speech signals in terms of acoustic characteristic rather than the segment points. Yeah. So the purpose of it is like you want to train the model to learn some kind of language that acts as text data, like a robot that can learn speech without learning how to write. Yeah. So that's basically the idea what I'm doing. So okay.
Sorry, guys. I was just going to say, the poll is up for everyone, so do answer the poll. But do finish up on what you were saying. It was, it's cool listening to what people are working on.
Oh, that's good. Yeah, thank you. Yeah, so okay.
So it's got a pull up, I think. I'm sorry, I disconnected. I'm connected to the screen. I work on large models optimization and inference right now, as you can see. And you can start very well. People are using the code, right?
Yeah, they're filling it. Yeah, correct. Last one, like what is monitoring and observability in the ML system. Also, we have we show some 1 or 2 case studies related to the cost of the ML system failures, and later we have a discussion in the future, like the current situation with generative AI. Fine. So the chapter takeaways. So talking about the cost of the ML system failures, there are 2 types of the failures that we can see from the book. The first one we call the software system failures. For example, we have some listed perhaps here. The first one will be the dependency failures. So this is kind of some when you use some supporting software or use some dependent packages or libraries, and they are somehow have some breaks like outdated or has some bugs or errors somewhere, and that failures can affect the workflow of the bigger machine learning system that are using them. The second one is the deployment failures. These types of failures, like, is more like when you deploying, I would call it deploying errors. Like, for example, you deploying your models on some computers, but later on the model needs to write something or needs to have some weak provision, but you lack of it. So, you don't have the data in the parallel breaks. Or you just use the wrong version of the model, so you produce the wrong outputs, or not updated outputs as expected. So even though it works, or sometimes it doesn't work, but you still call it deployment failures. The third one, we call it like the hardware failures. So this kind of failure is specific to the hardware. Like, for example, you can like have an overheat CPU when you train a model or you run a model on CPU. Usually not so usual, but yeah, in that case, the CPU can be overheat and the servers maybe broke up and hang out, suspended, whatever. So the model stop and the whole system stop. And yeah, so this kind of failures maybe a little overlap with the last one, which is the downtime failures. Like I have mentioned before, this is, for example, you have the server shut down, or because of some reason, some kind of electric shortage, or you have some component service like in a microservice architecture, you're using some component agents, component service. But some of the service like have some problem, like they just suspended or they stop working, and also the whole pipeline stops. So all these types of failures, like we call them the software system failures. So they're not really directly related to the machine learning model, but like, you still affect the whole system. And the second one, we have more specific ML, which also goes machine learning specific failures. And some of the cases we listed here can be, first of all, the mismatch of data distribution. This has been seen as maybe the most frequent failures in the ML system. The problem is when, for example, your production data, like the data that you use, and you maybe for continuous training, maybe for the inference in the production phase, and the data you use in the training phase, they're not in the same distribution. So sometimes your model performs very well on the training stage, but you give a pure performance on the production data. So this kind of mismatch distribution setup happens. The next one we have the edge cases. So this kind of failure